It's a real pleasure to be able to share some ideas, some work with you guys. The core of this presentation is about how do we achieve vendor agnostic architectures or SDN architectures more specifically using OpenFlow. So we look at two things. The key focus is around two things: the vendor agnostic part and followed by the TTP. In order to understand the complexity of the problem, right? So if you look at a typical network stack, it's not just about software. It basically starts from the ASIC, where pretty much most of the intelligence or the forwarding capability lies, followed by a more simplified form of programming those ASICs, which we call the data plane. And then a control plane to keep things dynamic so that you're not restricted to only certain ways of configuring your ASICs. So you have a control plane that introduces some logic, some method to change your data plane forwarding methods. And as you go further up, you have the management, the automation framework, and then an orchestration framework where you pretty much incrementally automate your network or your compute or your workflow essentially. So if you basically subscribe to a single vendor theory where a single vendor provides everything, there are benefits to it in the sense like you have one vendor to go and ask for support and get all your problems resolved. But the challenge is that single vendor, typically, no matter how big they have limited resources. So the things that you would want to achieve your network may not be addressed by the vendor, or it may not fall in their priority list. So pretty much what would happen is everybody would follow a single network architecture and pretty much lose any edge there is to actually deriving value from the network, right? So single vendor is good and bad in certain ways. So the whole community and the industry is now converging to the notion that if you were to disaggregate not all of them, but at least a few of these layers, you have the ability to bring in some value, some innovation at the network layer because you have additional resources that are thinking about the problems that you have that can actually provide you with a viable solution, right? So what that really means is that we have something called the network gap. The gap is ideally what I would like to coin as the difference between a typical innovation cycle, if you were to take the software innovation cycle and cycle, because of the openness, because of the number of contributors, collaborators that exist in the software industry, the innovation took off. The value that the innovation brought in for that industry is kind of huge, right? So if you look at big data, the number of services, the actual value that it provides to the business, back to the business, has pretty much exponentially increased. Whereas if you were to compare it with the network innovation cycle, because of this theory of single vendor, it was more or less restricted to what that vendor could actually deliver, right? So this gap is what we call as the network gap. And obviously, in order to solve or provide a solution to overcome this gap, you need to first identify those reasons. What exactly are those reasons? So when we went into the field and we tried to help customers build SDN architectures or deploy SDN architectures, there were three main things that the customers pointed out to us, which is not very new or unique. These are known things. Again, it revolves around the fact that the systems that they have today are, or the incumbent systems that they have today, are pretty much closed systems. That is, the network vendor completely rules that layer, that infrastructure, and only the innovation that he opens up is what is made available to the end customer. The second one is basically the number of protocols that are available, right? So it's a clear overload of protocols that can solve one simple problem. So if you were to take just IP routing, you have probably 10 or 15 protocols, and still they don't address all the requirements of the routing or forwarding the IP traffic. So how do you get around all these problems? Again, you have to get away or actually augment what you already have with additional capabilities. Again, because it's a closed system, there are, that innovation cycle is not there. And finally, for decades now, people have actually built systems based on these closed architectures or protocols, and that has pretty much driven them to a point of inertia that they have such a huge amount of legacy infrastructure that the move to a completely new paradigm or forklift upgrade is not even possible. It cannot be thought of. So how do you balance all these problems with the new way of working? There is obviously a solution available, right? So it's not a dead end. There is a solution available, and we enable our customers to move from their inertia, to move away from their current legacy infrastructure into more dynamic environment using TTP. TTP is, as you guys probably know, it's table type patterns. And what table type patterns essentially brings to the fore is the ability to expose your ASIC capabilities instead of just a certain table, which is the TCAM, to the OpenFlow or the SDN controller, right? So effectively, what you can derive from that is quite a few things. It's not just as simple as having a TTP implementation and everything goes fine. You have to enable it in a process, and the process is basically starts from the service design without actually incurring any cost of the infrastructure at all. You have a model that a customer can actually design their service around, right? So for example, if you were to design a layer 2 forwarding paradigm, there are probably 10 ways of doing that. You could use MPLS, you could use VXLAN, you could use some traditional layer 2 forwarding methodologies. But the idea is, how do you customize all that to your specific needs? How do you overcome certain issues that most probably your incumbent provider is not able to address in a timely fashion? So service design is a very important aspect of it. Then again, after you do the service design, the operational aspect of it is to actually program your network, to be able to make the ASIC do what you really intend it to do. So, and that has to be a normalized way. It cannot be, every time you change your ASIC vendor or every time you change your network infrastructure vendor, you have a different way of programming stuff. It has to be normalized. Otherwise, the effect of actually bringing in customization wouldn't work, wouldn't scale. So normalized ASIC programming is another big component of this. And finally, you get into the whole idea of provisioning and troubleshooting. So how do you operationalize once you have designed your service, once you have developed a program that can dynamically configure your network, how do you operationalize it in the sense of how do you extract the necessary analytics, be it alarms, be it counters, whatever are the information elements that you want to seek from the network infrastructure, and how do you create services out of it? It could be troubleshooting, it could be a provisioning ticket or whatever it is. How do you integrate it within your broad range of OSS and BSS functionalities? So all these things can be actually done even without incurring a single, even the slightest cost on the hardware. And the way to do it is TTP, right? Table type patterns. So what exactly is table type patterns? It's nothing but an ASCII file, right? So you have an ASCII file that pretty much details the pipeline supported by your infrastructure. And what do I mean by that? It's now getting to a little more detail in the sense like I'm trying to explain how we abstract the ASIC hardware into a programmable mode. So TTP is nothing but an ASCII file that allows you to understand in a very simple language how do you program a certain pipeline. So for example, you have a TTP that enables IP routing on the hardware, right? So it creates certain tables and then allows you to jump from one table to the other. That is the most simplest form of TTPs. So effectively, TTP gives you a way to work and design your service and get it operational. So you have two aspects, the development side and the operation side, and you can pretty much devise all the process involved just using this simple ASCII file. And the key point to note is, even before deployment, you can actually figure out whether the service that you have enabled can be brought into the function, can be brought into the operational circle at all or not. And if for some reason you don't have, there is no harm in rejecting that project because there is no cost associated with it. So now that we have something called this TTP, how can we use it, or where can we actually use it? What is the most effective way of using these TTPs? There are at least 4 different areas that we work with for our customers in order to enable them to create a single application, a single SDN application that would help them work across any ASIC architectures. Now, the key point here is to note that about roughly 80 to 90% of a network application is well known. What it means is there is a pipeline that is well defined. So if you want to do layer 2 forwarding, it's not rocket science. There is a layer 2 table that you're going to look up and make a forwarding decision out of that. If it is a routing application, the key point is you do a lookup on the VLANs, on the MAC tables, and the routing table, and do a forwarding lookup and make a forwarding decision. So if you want to cover those simple applications, you don't need extreme innovation, you don't need extreme thought process around it. If you have one abstraction layer that is going to allow you to program those forwarding paradigms across any architectures, that's already a big win, right? So you don't have to think what kind of hardware you need to procure. All you need to be aware is that you have a simple forwarding paradigm and you can enable it on any ASIC architecture. So that is the key enabler that TTP allows you to do, right? So whether it is a data center networks, overlays, or just a form of open networking, which allows you to bring in multiple players, multiple vendors within your network, your application doesn't change. Your application stays the same. And then a multitude of SDN solutions where you have the ability to interface with multiple controllers, for example. So if you divide your the SDN application across multiple controllers because of the benefits that you may derive, you can choose to do so without actually thinking about your networking infrastructure by using this TTP profile. So TTP is the key enabler for most of these SDN applications. So what I will follow up with is some of the changes that we have made, some of the problems that was identified, and what helped us to shape what TTP is today, right? So if you look at some of the current implementations of forwarding in most of the open vendor switches around the OVS model, around the OpenFlow model, you have a singular type of forwarding decision that you can make. What I mean by that is you have a single resource, the TCAM, that is made available to be programmed using OpenFlow, right? So all your entries that you create, the flow rules that you create, are programmed in the TCAM in such a way that they would make a single hop lookup and then derive the forwarding instruction or forwarding decision and move along. Now, there are certain issues with that model, right? So if you look at it, clearly the ASIC has a lot more resources than just the TCAM. And actually the TCAM is a very limited, restricted resource. So in order to leverage anything in OpenFlow, you basically are underutilizing either the ASIC or the capabilities of OpenFlow itself, right? So either way, if you look at it, you're working with either a limited resource or you're restricted in your OpenFlow capabilities and your applications. Another way to look at it is TCAM is pretty much a priority-based lookup table, right? So it may not be extremely effective if you're going to scale up your networks. Like for example, if you have 100,000 routing entries or layer 3 entries in your table, then a top-down approach of trying to figure out where the match is not going to work. And this problem has pretty much been solved like a decade back when they introduced longest prefix matches and other sophisticated algorithms that pretty much work on standard memory devices. So clearly, OpenFlow was missing that ability to scale. And finally, the other thing is, if you were to really focus, if your application really is TCAM based, then the cost of that solution goes up because TCAMs are expensive devices. They don't scale too well. In order to build a TCAM-based network infrastructure, your cost of the solution is going to shoot up tremendously. So OpenFlow used to have this limited resource to work with, and hence its penetration into mainstream deployments was very, very restricted. So what does TTP bring to the table? This is a very a simplified but a very good use case that we have enabled some of our customers with. It's a unicast routing profile. So TTP essentially, everything that you see in the horizontal line is a table, right? So as you can see, there are tables 0, 10, 20, 30, 40, and more as we kind of bring in. But clearly, we exposed these tables as a unicast routing pipeline. So effectively, you can make any routing decision using such a pipeline. So what are the key differences from the previous instance of OpenFlow and TTP? The first thing is we enable multiple VLAN tables, multiple ASIC tables via OpenFlow, most notably the VLAN, MAC, IP, and the TCAM tables, right? So using these tables, you can create effective indirections that will allow you to make intelligent decisions. Like for example, when a packet comes in and hits the VLAN table, you have the ability to basically punt it to the next table, which is the MAC table, or you can actually put it onto a policy table, right? So you can make those kinds of decisions. Now again, this is very dependent on the flexibility of jumping from one table to the other is the key difference that the ASIC architectures or ASIC vendors kind of bring about, right? Some ASIC vendors, they provide you with the traditional architectures of a fixed pipeline. So you cannot be extremely innovative in how you kind of jump through the tables, but they allow you only certain flexibilities between the tables. And there are yet other architectures or other ASIC vendors that allow you complete freedom of jumping from any table to anywhere, right? So that is one of the key things that enables us. But what we figured is for a unicast routing pipeline, no matter what ASIC architecture you pick, you pretty much 80% of the time are going to travel through these pipelines that you see here, this pipeline that you see here, right? So what this routing pipeline enables you to do is not only just perform unicast lookups and unicast routing, but it allows you to do load balancing. So if you look at this particular box here, what it signifies is that you can create a group action wherein the lookup happens on multiple entries, and you can create a flow such that it can be forwarded to multiple ports or load balance across multiple ports within your switch using TTP. So a single pipeline effectively, even though I call it a unicast routing pipeline because that is what we have enabled our customers with, the same pipeline with the group actions can actually do the multicast routing functionality without any change, right? So this allows you to pretty much program your network on demand. And the same group action can also bring you load balancing functionalities or active standby kind of functionalities in your egress port. So just with this single pipeline, I'm able to allow the end customer to manage how he wants to forward the traffic in multiple ways. The other benefit that this clearly gives us is the fact that now since the layer 3 table is actually an IP table, you have the ability to do a longest prefix match, which is what the incumbent providers actually give you as a benefit, as an efficient way of doing routing. So in OpenFlow, using TTP, you basically enable that using the same layer 3 table that an incumbent provider or a traditional network vendor gives you. And finally, because of that ability, we are able to scale from something like a TCAM resource. Typically, in most of the white boxes that you find, the TCAM resources are somewhere between 1,000 or 2,000 entries. And of course, if you slice them, you get more, but effectively you are between those two numbers for most part, right? So by exposing the layer 3 tables, now for a routing application, I can scale up to 100K or 200K flows using the same ASIC, right? So suddenly your OpenFlow application now looks like, it could pretty much behave like a traditional routing implementation using the same ASIC. And the real good part is that this does not require any enhancements to the ASIC. This is just a software layer. So just by introducing a TTP concept within your network infrastructure using OpenFlow, you are able to leverage pretty much the scale capabilities, the traditional routing lookup capabilities for an OpenFlow or an SDN-based application, right? And a similar thing can be extended to an MPLS concept as well. Now, the biggest problem with MPLS is the fact that it has a very complex control plane. You have the P routers, the PE routers, an LDP protocol, and on top of that, a BGP protocol, and 10 other things to allow you to define what is the right path to take for a certain traffic, right? Now, you may never need all that complexity in your network to actually enable something like MPLS using the TTP. It could be a very lightweight thing. The fact that you're centralizing the control plane into an SDN controller allows you to build your own control plane around the MPLS data plane, right? So you could have a very lightweight MPLS control plane, allowing you to navigate through the typical tables, the MPLS tables, and create a forwarding decision. Again, this particular table represents a VPLS pipeline wherein there are 2 label lookups instead of 1 for the VRF. So if you want to really create a VPLS pipeline, all you need to do is use a JSON file that the TTP profile is provided with, and then use what exactly are the tables that you want to navigate through. And you can very, very effectively create a dynamic service kind of a model. You don't have to restrict yourself to something like a VPN routing application or a layer 2 VPN application. But you can actually extend this to do even service integrations, right? So you can create a service chain model around this. You could do pretty much a whole bunch of functionalities is what you can integrate just by enabling the MPLS table access for OpenFlow. So for a lot of such applications where customization is required or the scale is required, TTP is an excellent way of kind of enabling those applications. And these are not just theoretical. We actually have a customer who has integrated an entire solution. It's a bit more involved, but the key point is there are certain elements that are kind of required in order to make the SDN application scalable and truly multi-vendor capable, right? So if you look at it, pretty much they were using our OS, the PIC OS, on top of ASIC vendors like Broadcom and KVM, and we expose OpenFlow and OVS DB APIs to the northbound, which is basically the controller. And the controller is where the applications reside, pretty much, or the network services, for example, that's where it resides. They had a network orchestration layer to integrate all this into their current infrastructure, so effectively giving them a transparent view between the legacy infrastructure and the new infrastructure, which is OpenFlow capable. And finally, the SDN applications, it could be BGP, firewall, traffic engineering, or whatever analytics to kind of derive from the network infrastructure. They built it as an agnostic layer that works across all their infrastructure, right? So they didn't have to effectively change any of these applications that they had built across the legacy network or the new SDN-enabled network. So that effectively gave them a very smooth migration, a very transparent experience when they were trying to deploy a SDN-based network. And obviously, TTP is the key element that enabled them to do this. So what were the benefits that we realized because of TTP? The first and the most effective one is the scale. So effectively, if you were to go from a TCAM, which is at best a 2K scale, you could go up to 2 million using something like a KVM chipset, right? So depending on your application and scale needs, you could effectively choose a Broadcom chipset or a KVM chipset and enable the scale of your deployment without ever having to touch your application. And nothing is compromised. Everything is available at line rate. Just because we are introducing TTP doesn't mean that we are affecting performance in any way. We retain the performance, line rate performance, pretty much hardware acceleration at that point. Security, security is really a problem if you are working with an untrusted resource or an untrusted domain within your network. For most part that we have seen in data centers or even in the WAN, when you pretty much own the infrastructure, the optical network or anything, security is really not a concern. And even if you were to need security tools, Linux is quite an evolved platform where it's fairly secure. You can build a security infrastructure around the Linux platform to make your network more reliable and more averse to any security threats. The biggest thing was about interoperability. The whole idea of TTP is that you're going to extend the same functionality that an incumbent vendor pretty much locks up within his ASIC or his architecture in a more open and programmable way. So that allows customers to kind of think about multi-vendor architectures in a more seamless manner. And then simplicity. As we actually saw, once the customer actually created his application, whether it is a simple routing or a traffic engineering application, they didn't have to change or meddle with it by changing the network infrastructure vendor. So that was a huge plus. It was really very simple to understand that with the TTP, you are able to kind of access all the forwarding tables within the ASIC. And the SDN application actually using the same logic they used to use in a traditional network infrastructure. So we went a bit ahead and tried to compare ourselves or grade ourselves to a traditional infrastructure, because that is extremely important, right? So how do you grade yourself with a current infrastructure that the customer has? So in most cases, we kind of are at par with the incumbent infrastructure. There is nothing unique or different that the current infrastructure would do for a typical routing application. The places where we are better is actually in doing interop, that is being able to work seamlessly across all varieties of ASIC architectures or ASIC vendors, and then actually be able to use the same applications built across all these varying network infrastructures. So those were the two clear benefits that were immediately realized once we enabled a customer with the TTP model. The next few slides are about, I'm going to talk about some of the use cases that the single TTP file can enable. Like we have the unicast routing TTP, and that TTP alone enabled quite a few use cases for our customers, right? So if you look at a typical top-of-rack solution where you have a fabric, a data center fabric, and the top of rack is the only place where the customer chose to actually put in OpenFlow. So effectively, the spine is still a traditional IP routing spine, nothing special, no special needs there. The only place where he wanted to innovate was at the top of the rack. So effectively, depending on the workloads that they had, in this case, it was a virtualized service. They wanted to enable programmability and dynamic pipelines on the top of the rack, depending on a particular service they wanted to instantiate. So the same unicast routing TTP that was discussed earlier, that was able to provide them with the dynamic ability to stitch particular segments to enable routing on demand, for example, on the top of the rack, or switching on demand on the top of the rack. So that allowed this customer to effectively stitch together network applications or virtualized services to someone via the internet, right? The second use case is around the border leaf itself. This is another huge application where scale is of prime importance, right? It's not just about the OpenFlow functionality, but how do you get scale with all the applications that you have. The other part is the border function is typically a more specialized function, so you might want to actually run a completely different or a separate controller with a specialized application that effectively controls the border leaf. And even though it is a common fabric, as you can see, you have the ability to partition your fabric by using different controllers, using the SDN concepts. So we were clearly able to enable that model using OpenFlow and TTP effectively to bring in scale at that layer. And I think one of the most popular services that people want to use is, besides creating your underlay, how do you actually create an overlay service on top of it, right? The previous two use cases kind of talked about how do you dynamically control your underlay. And this particular thing is talking about how do you actually join workloads together across this underlay. So even overlay, it's a matter of encapsulation that you choose to use that you define your overlay on. So even for the overlay, we provide the ability for the top of racks to kind of offload the overlay from your hosts and basically create a network across your WAN network so that you have a single homogeneous network environment for your particular workload or your particular private cloud infrastructure. So effectively, at all these layers, once OpenFlow is enabled at all these edge layers, you are able to derive the benefits of being able to program those layers, stitch those layers together, and with the help of TTP, you are able to define your dynamic services at that layer at scale, right? So all this is made possible using TTP as a baseline and the flexibility of OpenFlow to effectively instantiate those services. And finally, the whole idea is to basically, the key benefit to derive from this is to move away from the lock-in, right? So as you could see, the applications were not extremely complex to deploy. So we had a kind of an edge because we were able to kind of show the benefits of using TTP in a simplified application, but it could easily get extremely complex depending on how much complexity you introduced in your control planes and what are the different forwarding models you want to do. So the first benefit to realize is there is no lock-in anymore, right? You move away from that. You use TTP to effectively achieve the scale and the true ASIC capabilities are exposed because of the TTP. And finally, you have the ability to stitch together any of these segments that you create, whether it is the data center, whether it is the WAN, or whether it is an overlay network. You have a single control plane or single control plane layer effectively to configure all these services dynamically. And that is the true benefit of actually using TTP, and gives us the idea of made to order. So depending on your specific requirements, you could use TTP in any of its flavors to build a network, based on your requirements. You don't have to absorb all the complexity that comes in with the traditional vendors. You just build exactly the network that is required by your functions, your network infrastructure. And that is the key message we had today. So thank you for the time. And if you have any questions, I might probably take it. We still have about 5 minutes. Yeah, please. Yes, we do. Actually, I have a blog that is there. So that will give you some reference of exactly how the TTP file looks like. I can send you a pointer offline if you really want to access it. Any other questions? Yeah. Yes, the slides will be available publicly for download at a central location. I'm not sure where, but yeah. Yeah.
I'm still confusing between TTP and people like Torrent HC.
Right.
What is the difference?
Right. So P4, as you said, it's a programming language. TTP is more like an ASCII file that details all the pipeline, right? So they are different in the way that since it's a programming language, it has to be compiled at boot time, whereas TTP is an ASCII file that you can associate, at any point in your network lifecycle. So for example, TTP in this case, if you go to my blog, there is details of how to configure the TTP. It's in case of PeakOS, you have a simple OF VSCTL command that you can associate a TTP file to your bridge, and then that TTP is available for you to configure, right? And that pipeline is available for you to configure. Whereas P4 is a compiled language, so you have to pretty much determine what is your data pipeline ahead of time before you actually compile that stuff. Yes, please.
The IP version for routing TTP that you're using, is this the same as the one that's being proposed for Material?
Yes. It is pretty much the same as what we are using for Atrium. That's definitely a baseline for the TTP, but we have added a few more functionalities like the QoS actions and the color-based actions and all that kind of stuff. But it's pretty much based on the Atrium TTP.
Have you made this TTP available publicly?
Not yet, not yet.
I'm sure the OPWG would be interested to look into.
I'm certain. So that's our next step to go to. I mean, the idea here was to actually enable a customer and kind of present the use case, but I completely get your point. Yeah. Yes, please.
One question. For the South Mountain interface, such as controller and forwarding your interface,
Yes.
inspect overflow. We also need such as the OS config. So here TTP is only for overflow. Is that correct?
So TTP is not bound to any of the protocols between the controller and the switch. It's a file that you could use. So effectively, you could use OVS-DB as well. So it can be extended to OF-config. It can be wrapped around any protocol that you have. So it's not bound. The use case that we have enabled here is OpenFlow based, right? Any other? Perfect, thank you. So if you have any further questions, please find me. I'll be around here. We have a booth in the exhibit hall as well. So I would invite all of you to come and have a talk with me if you're interested to learn more about TTPs. Thank you.